minimum height trees looks innocent. Until you try every root and blow up to ON squared. Phong interviewers love this because the optimal trick is stunningly simple. Peel the tree from the outside in until 1 to 2 centers remain. Master this, and you'll be ready for graph center/diameter problems on the spot. Let's attack it with basics. We're given n nodes labeled 0, n1 forming a tree, connected, acyclic, and an edge list. We need all node labels that can be roots producing minimum height. A tree's minimum height roots are exactly its centers, 1 or 2. Brute force, run BFS/DFS from each node to compute height ON squared. Instead, observe, if we trim leaves layer by layer, like topological sorting, the last 1 to 2 nodes left are the centers. Why? Because removing leaves doesn't change centers. We're shrinking toward the core. Complexity. ON time and ON space. Handle tiny cases. If n less than or equal to 2, return 0, n1. Build an adjacency list and a degree array. Initialize a queue with all leaves, degree 1. While more than 2 nodes remain, pop current leaves, reduce neighbor degrees, and collect new leaves. Return the last batch of nodes in the queue. They're the centers. Time complexity for this approach is ON, where n is the number of nodes. The algorithm removes leaf layers one by one, touching each node at most once, making it very efficient. We use a method called topological trim, or peeling leaves. The idea is that a tree's center gives the minimum height when chosen as a root. Instead of checking every node, we peel off the leaves layer by layer, like peeling an onion. The outermost nodes are removed until only the center, or 2 centers, remain. These remaining nodes are the roots of the minimum height trees. This approach avoids deep recursion or brute force checking and remains efficient even for huge trees. In our Java solution, we start by defining a solution class to wrap the method. The main function receives the number of nodes and all edges. If there are no nodes, we return an empty list. If there is only one node, it's automatically the root of the minimum height tree. We prepare a graph structure, where each index stores the neighbors of that node, and fill it with empty sets to later add connections. We also create an array to track each node's degree, essentially counting how many neighbors each node has. We loop through all edges, adding connections in both directions because the graph is undirected, and update the degree counts for each node. Next, we prepare a queue to store all leaf nodes, those with a degree of 1. We loop through all nodes, adding any leaves to the queue. We also keep track of how many nodes remain in total. As long as more than 2 nodes remain, we keep peeling off layers of leaves. For each round, we count the leaves, subtract them from the remaining total, and process each leaf one by one. For each neighbor of a leaf, we remove the leaf from its neighbors list, simulating that it has been peeled off. We reduce the neighbor's degree, and if it becomes a leaf, we add it to the queue for the next round. Once only 1 or 2 nodes remain, these are the centers and the roots of the minimum height trees. We return them. And that's how this algorithm works. It builds the graph, identifies all leaf nodes, and repeatedly trims away leaf layers until only the center nodes remain. Efficient, simple, and elegant. Each leaf is removed only once, and each edge is processed only when its leaf is trimmed. The algorithm stops when the centers remain, giving a worst-case runtime of ON. Now that we've implemented our solution to find the minimum height trees, it's time to test it with an actual input. This helps us see how the algorithm trims leaves from the tree level by level to identify the root nodes that produce the minimum height. We'll walk through the input, observe how the leaves are removed, and confirm that the output matches the expected result. Let's test the function using this input. We have n equals 4, representing 4 nodes labeled from 0 to 3, and an edges array defining the connections between them. This tree structure forms a star centered at node 1, which connects to nodes 0, 2, and 3. Here's why the solution works. The algorithm builds a graph and counts the degree of each node. It then identifies the initial leaves, which are nodes with only one connection. One layer at a time, it removes these leaves and updates the degrees of their neighbors. This process continues until at most 2 nodes remain. Those remaining nodes are the roots of the minimum height trees. For this example, the initial leaves are 0, 2, and 3. After trimming them, only node 1 remains, which is the root of the minimum height tree. And that is exactly what the program outputs. 1. This verifies that the code works correctly and passes this test case. So our implementation is correct. The algorithm successfully identifies the center nodes that minimize the height of the tree. It handles the given structure accurately and returns the expected output. The BFS-style trimming ensures efficiency and guarantees that the minimal height roots are found. Time complexity for this approach is ON, where n is the number of nodes. We only need 2 BFS runs plus a path reconstruction, so the algorithm runs in linear time. We use a method called find diameter and return middle. The idea is that a tree's diameter, its longest path, holds the key. The center or centers of that longest path are the roots of the minimum height trees. Here's how it works. We first run BFS from any node to find the farthest node, which we call node A. Then we run BFS again starting from node A to find the farthest node from it, which we call node B. This gives us the diameter of the tree. We then reconstruct the path from A to B, and the middle of this path, one or two nodes depending on the length, are the centers of the tree. This method avoids trimming leaves and goes directly to the geometric center. In our Java solution, we start by defining a solution class to wrap everything neatly. The main function receives the number of nodes and all edges. If the tree has 0, 1, or 2 nodes, the answer is straightforward, and we return immediately. We build an adjacency list to represent the graph, adding an empty list for each node and filling in its neighbors from the edges. Then we run BFS starting from node 0 to find the farthest node, node A. A second BFS run from node A finds node B, giving the diameter. We also keep a parent map to reconstruct the path from A to B. We walk backward from node B using the parent map to build the path. Once we have the path, we determine its length. If the length is even, the tree has 2 centers, we add both middle nodes to the answer. If the length is odd, there's a single center, the exact middle node of the diameter. Finally, we return the center or centers of the tree. The BFS helper function creates a queue and a visited array to track nodes, and a parent map to reconstruct paths. It enqueues the start node, marks it visited, and tracks the farthest node as it explores all neighbors. Once BFS completes, it returns the farthest node along with the parent mapping. And that's how this algorithm works. It builds the graph, finds the diameter using 2 BFS runs, and returns the middle of that longest path. Efficient, simple, and elegant. 2 BFS passes are enough to find the diameter. The middle of the diameter gives the minimum height tree roots. Path reconstruction is linear. No extra complex data structures are needed, and the worst-case runtime is ON. Before checking the output, let's understand the problem. We are given n equals 6 nodes edges equals 3, 0, 3, 1, 3, 2, 3, 4, 5, 4. The goal is to find all roots of minimum height trees, nodes that produce the smallest height when chosen as tree roots. Let's test our function with this input. Here, we have a tree with 6 nodes, connected as described by the edges. Here's why the solution works. Build the graph. Represent nodes as adjacency lists. Use BFS to find tree diameter. First BFS from any node, here, node 0, finds one endpoint of the diameter, Nadia. Second BFS from Nadia finds the other endpoint, Nodeb, and keeps track of parent pointers to reconstruct the path. Identify middle nodes. The diameter path is the longest path in the tree. Nodes in the middle of this path are the roots of MHTs. If the path length is even, there are 2 middle nodes. If odd, 1 middle node. Step by step with this input. BFS from 0 farthest node is 5, BFS from 5 farthest node is 3, diameter path, 5, 4, 3, 0, or similar middle nodes, 3, 4. These nodes will produce minimum tree height when chosen as roots. And that is exactly what the program outputs, 3, 4. This confirms our code works correctly for this test case. So, our implementation is correct. It successfully identifies MHT roots, efficient, accurate, and reliable. Our implementation is correct. It accurately finds the diameter of the tree. It correctly identifies middle nodes as MHTs. Let's wrap up the minimum height trees problem. At first, it seems like you just need to pick the best root, but trying every node quickly explodes into ON squared. The clever trick here? We don't search from the roots outward, we peel the tree inward. Breakdown recap. We're given n nodes forming a connected, acyclic graph, a tree. Our goal is to find all possible root nodes that produce the minimum height when the tree is rooted there. In simple terms, we're looking for the tree's centers, the points that minimize the longest path to any leaf. Assess recap. The brute force approach would be to run BFS or DFS from every node to measure height, but that's too slow. Instead, we realize that the tree's centers can be found by trimming leaves layer by layer, just like peeling an onion. Each round, we remove the outermost leaves until only 1 or 2 nodes remain, which are the centers of the tree. Structure recap. We handled small cases first. If there are 2 or fewer nodes, we just return all of them. Then we built an adjacency list and tracked the degree of each node. Next, we added all current leaves to a queue, and while more than 2 nodes remained, we kept removing those leaves, updating their neighbors, and collecting new ones as they appeared. The final remaining nodes are our centers. Implement recap. After coding this peeling logic, we ran it on LeetCode, and the solution executed smoothly without any errors. Check recap. We verified it across multiple test cases, and each time, the output correctly identified the minimum height tree roots. Closing insight. The big lesson? Sometimes, finding the center of a problem means working from the outside in. By trimming layer by layer, we let the structure reveal its own core, efficiently, cleanly, and in linear time.